Gnanam paramam dheyam. Knowledge is supreme.
We are in the last phase of discussion of electronic spectroscopy, and right now we are doing a case study. Yesterday we have talked about the electronic states and transitions of benzene, and in doing that we have talked about something called vibronic coupling. Today we want to see what the spectrum actually looks like and how far we can go in interpreting what the bands are due to. How far we can go in assignment of the electronic absorption spectra bands of benzene, right. But before that, this is a summary of yesterday's discussion. What we have said is this: we have understood the symmetry of the pi molecular orbitals of benzene, and from there we have said that the ground state of benzene, not very surprisingly, is singlet A1G, because all electrons, all occupied molecular orbitals are doubly occupied. As we have learnt earlier, that corresponds to a totally symmetric electronic state. Then we talked about a HOMO to LUMO transition. So, one electron goes from the highest occupied pi bonding orbital to the lowest energy erstwhile unoccupied pi star bonding orbital. We do that in the language of symmetry. The transition is from an E1G orbital to an E2U orbital. So, the electron configuration now is E1G3, E2U 1. So, even out of these E1G orbitals, one is doubly occupied, one is singly occupied, and one of the E2U orbitals is singly occupied. And as we know, when we have two orbitals that are singly occupied, the symmetry of the state is given by a direct product of the symmetries of these singly occupied orbitals. So, we had done a direct product of E1G and E2U, and we had seen, using the product table of D6H point group, we had seen that we get three states: E1U, B2U and B1U. And of course, these two electrons are now in two non-degenerate states. So, you can have singlet as well as triplet combinations. So, we end up generating 6 different states, but as of now we do not know what the relative ordering of energies are. We have to do it, as we said yesterday, by a more rigorous quantum chemical calculation, and by the time we are done with the discussion today, we will see that we have an experimental way of determining not only the order, but also the absolute values of these energies from the spectrum of benzene. Okay. Then we wanted to see what are these states. First of all, we are talking about transitions that are spin allowed. We are going to encounter one transition that is spin forbidden, but as we know, spin forbidden transitions have very small values of transition probability or molar absorption coefficient or extinction coefficient, whatever you might want to call it. So, for now we limit our discussion to singlet transitions. The ground state, as we agreed, is A1G. Excited states are E1U, B2U, B1U. So, when we talk about singlet A1G to singlet E1U, singlet A1G to singlet B1U, singlet A1G to singlet B2U, we ask the question, which of these transitions are allowed and which of these transitions are not allowed. And to understand that, we go by the usual route. We need to know the symmetries of x, y and z coordinates, because we have to work out the symmetry of the triple product. The three factors involved in this triple product are the wave function from which the transition originates, the destination wave function, and one of the components of the dipole moment. So, x or y or z. That is what we did here, right. The initial state is just that in Harrison-Bertolucci's convention, they do not write psi 2 mu psi 1, they write psi 1 mu psi 2. For the purpose of direct product, it does not matter. So, A1G in all the three cases denotes the symmetry of the ground state. E1U, B1U, B2U are the symmetries of the excited state formed by HOMO to LUMO transition, and A2U denotes what? A2U is Z, right, and E1U contains X as well as Y. E1U, as you know, is a two dimensional representation. So, X and Y jointly form the basis of this two dimensional representation. So, what we did is we worked out these triple products in all the cases, and we saw that only in the case of A1G to E1U transition through XY we get something in A1G. So, we said that only singlet A1G to singlet E1U is fully allowed and is XY polarized. The other two transitions, singlet A1G to singlet B1U or singlet A1G to singlet B2U, are orbitally forbidden. After this, we embarked on the discussion on how it might be possible for orbitally forbidden transitions to become vibronically allowed. And this is what we had said. When we wrote the expression for the transition moment integral, we wrote it like this. Alright, but suppose you cannot separate these two, then the integral you have to worry about is something like this. So, we are talking about a situation where Born-Oppenheimer approximation does not work anymore. You cannot separate the coordinates of electronic and vibrational motion, they are entangled. Of course, what you should ask at this point is, why will I even write these wave functions like that? I should ideally write something like psi v dashed e dashed and psi e v, alright. But then those of you who have studied perturbation theory will know the way everybody has studied, so everybody would know the way we handle this is that generally when we have a situation like this, we expand it according to Taylor series, right, and then if you write this as a perturbation term, then the product of the increments actually is too small to be considered. So, you can still get away by using a product of wave functions as long as you recognize that the coordinates are not separable anymore. So, this is the integral that you have to work with if you want to talk about vibronic coupling. Vibronic coupling means coupling of electronic and vibrational motion. Coupling means you cannot consider them separately anymore, they talk to each other. So, here vibrational and electronic coordinates actually talk to each other, they cannot be disentangled. So, this is what it is. Now, if I want to work with this integral, then essentially what I am saying is that I must worry about this product of all these wave functions and component of the dipole moment. This product must contain the totally symmetric representation. If that is the case, then the transition which is orbitally not allowed can be vibronically allowed. Are we okay so far? Then let me take this and let me write like this: psi v dash psi e dash x y z psi e psi v. We need to determine the symmetry of this, alright. Don't we already know what is the symmetry of this triple product, right? If you come back to a specific example, for A1G to E1U transition, the triple product is A1G cross A2U cross E1U, that gives you E1G, or A1G cross E1U cross E1U, that gives you A1G plus A2G plus E2G, right. So, we already know what the symmetries of these triple products are for benzene that we have worked out. So, what we need to worry about is, suppose this is something gamma I, we need to worry about psi v dash, gamma I, psi v, this triple product. And then what we also said yesterday is that we are going to worry only about 0,1 dash transition. 0,1 dash means vibrational level for the lower electronic level is V equal to 0, vibrational level for the destination level is 1. The destination level is usually denoted by a dash, V dash being 1. So, 0 to 1 dash, this is the one that you will see all the time, right. 0 is the only level that is populated at room temperature, and if you work at higher temperature, what we will consider is 1 dash to 0. I am not trying to say that 0 to 2 dash, 0 to 3 dash will not take place, they will take place, but for our discussion here these two are enough, alright. So, if that is the case, we know very well, suppose I work with this situation 0 1 dash, what is the symmetry of psi v in that case? It is totally symmetric, right. V equal to 0, this we have discussed this earlier when talking about normal modes of vibration. This is the same symmetry, this is totally symmetric. So, in this case I will just write A1G. What is the symmetry of psi v dash if v dash is equal to 1? Yeah. What is the symmetry of psi v dash if v dash is equal to 1? Same as that of the normal mode. Remember from our discussion of normal mode, same symmetry as xi. Now, the convenient thing is, since we have A1G already, I do not even have to worry about this. My only concern is this xi and gamma I. Understood? Now, tell me, when will the direct product of the symmetries of xi and this gamma I contain a totally symmetric representation? We have derived this small working formula earlier. When will they contain a totally symmetric representation? When they are the same, right. If the symmetry of normal mode is the same as gamma I, then your then the direct product will contain a totally symmetric representation, and therefore, the transition that is orbitally forbidden will become vibronically allowed. Okay? This is what we had discussed yesterday. So, now you see, with that background, now we can talk about whether any transition in benzene that is orbitally disallowed can become vibronically allowed. What about the first one? We do not even have to worry about the second one, right. Singlet A1G to singlet E1U, we do not even worry about that. Actually, we do not worry about the first one because already it is allowed. Let us talk about the second one, singlet A1G to singlet B1U. This has turned out to be B2G and E2G. So, what kind of vibrations are required to make this singlet A1G to singlet B1U vibronically allowed? Vibrations of which symmetry? Either B2G or E2G, agreed? So, this singlet A1G to singlet B1U, which is orbitally forbidden, can become vibronically allowed by coupling with B2G and E2G vibration. Similarly, the singlet A1G to singlet B2U can become vibronically allowed by coupling with B1G and E2G vibrations. Simple. Okay. So far so good. I hope everybody has understood everything. Any question? Any question? If not, what is the next question to ask? What would the next question be? We have established the conditions for which these orbitally forbidden transitions can become vibronically allowed. You have to have vibrations, vibrational normal modes of certain symmetries. So, of course, the next question to be asked is, does benzene have normal modes of vibrations of those particular symmetries, right? I hope we can all work it out. Symmetries of normal mode we have learned, right? How many normal modes of vibrations will be there for benzene? Yeah? Okay, 3n minus 5 or 3n minus 6? And what is n for benzene? 12 or 6? Sure? Not 6? So, 3 into 12 minus 6, how much is that? 30. In one of the questions, in one of the exams, I have forgotten whether it was 442 or 801, I had actually said this question, find out the symmetries of normal modes of vibration of benzene. Okay, it is a valid question, but for now we do not have to do it, I will just give you the answer. This is, so this is the question to ask, right? The answer is this, we will come to that a little later, sorry. So, in a while I will show you what are the normal modes of vibration that are there for benzene, but before that, this here is the absorption spectrum of benzene. Does it look weird or not? It looks weird to me. Can you tell me why it looks weird? The answer is there. If you look at the spectrum, you can figure out why it looks a little weird. It does not really look like the absorption spectra that you have seen. Yes? It does not look weird. That is a safe answer. Vishwarup, why does it look weird? Look, y axis is in log. It is a semi-log plot. Why is the y axis in log? When do we draw semi-log plots? When do we have a logarithmic scale? Yes? Easier answer. When do we draw log scale? When we want to show the small intervals and large intervals together in the same plot, because the moment you take log, what happens is the smaller numbers get amplified. See, this is your 10 to the power minus 1, this is 10, no, this is 1, this is 10. So, all this part is actually magnified and the upper ones are kind of shrunk. So, if you want to see small numbers as well as large numbers together, then you use a log scale, and that is exactly the reason why this is plotted in log scale, so that we can see strong transition, strong bands as well as weak bands, alright. The biggest one is this, and what is the value there? Almost 10 to the power 5, isn't it? So, 10 to the power 5, when epsilon is 10 to the power 5, what kind of a transition is it? 10 to the power 3 to 10 to the power 5, we have discussed earlier, is a fully allowed transition. So, we can assign that band directly to fully allowed transition. What is the only fully allowed transition? Singlet A1G to A1U, E1U, right, you are right. So, singlet A1G to singlet E1U. So, already with whatever we have discussed so far, we can assign the strongest band that is there in benzene, but usually that is not the most useful band. You know why? Because look at the wavelength, it is somewhere between 150 and 200 nanometer. Usually we do not even work at such wavelengths unless you can work in vacuum and all that. What is the next band? It is somewhere here around 200 nanometer. This is orbitally forbidden because it is a little smaller, and this band is definitely orbitally forbidden because your epsilon is only 10 to the power 2. But then you know what? This is really the most important band in benzene. What is the region? 250, 260, 240, right? This is called the benzenoid band. In fact, if you have any compound which has an aromatic ring, this is a band that you will always see. Okay. It looks a little different in solution phase, this is a gas phase spectrum, but then and also it is semi-log, but this 250 to 60 nanometer is where all aromatic compounds have an absorption. So, that band is a mark of aromaticity. So, it is most important, it is a benzenoid band, and as you see it is an orbitally forbidden transition. So, we want to find out which one it is. There are two candidates, right? We want to know which one it is, and this one of course is really very small, right? Had we not made a semi-log plot, we would have missed it. It is like 10 to the power minus 3, that is obviously a spin forbidden transition, alright. So, this is the spectrum that we are trying to understand. Now, if I take a closer look at the benzenoid band, this is what it looks like. Now, it is not semi-log anymore, y axis is now linear. So, it looks a little better. So, the question is what is the where do I get this band from, which transition? As you know, since it is an orbitally forbidden transition, there are two candidates. One is singlet A1G to singlet B1U, the other is singlet A1G to singlet B2U. and we know that they would become vibronically allowed by different kinds of vibration. Now, this is what I had kind of jumped the gun and started talking about a little while ago. Now, I will show you a list of normal modes of vibration of benzene. I will show you the symmetries as well as energy. Anything in bracket is theoretically calculated energy, anything not in bracket is experimentally observed energy. Here goes. Okay. So, what are we asking? We are asking, do we have B2G vibration? Do we have E2G vibration? Do we have B1G vibration? Okay. What is the answer? There is no B1G, right? Benzene does not have B1G vibration. What about B2G? Do we have B2G? Yes. Where are they? Here. I am using a wrong file. Anyway, these are the B2G vibrations and these are the E2G vibrations. Okay. Let me arrange it a little bit, and this is what the situation is. This is the benzenoid band we are trying to understand. We have a couple of B2G vibrations. We have actually 4 into 2 8 E2G vibrations, and we are trying to understand which one is it. If it is singlet A1G to singlet B1U, then it will be vibronically allowed by B2G and E2G vibration. If it is the other one, singlet A1G to singlet B2U, then it will be vibronically allowed only by E2G vibration. Okay. So, let us see how we can go about solving this riddle. To do that, first question we ask is, do you see which one is the lowest energy band here? Which is the lowest energy band? This one, the one where we have written H, right, that is the lowest energy band, right, because here you have lambda 240, 250, 260. So, longer lambda means smaller energy, that is your lowest energy band. What is this lowest energy band due to? It cannot be a 0-0 dash transition, can it? Because 0-0 dash transition is seen only for orbitally allowed transitions. As we have discussed earlier, this is not an orbitally allowed transition, it is vibronically allowed. If it is vibronically allowed, you cannot have a 0-0 dash transition. Are we clear about that? It has to be 0-1 dash or something like that. So, what is it? Now, I have to give you a little bit of additional information, and that will explain why of all letters we have written H there. That information is, this band shows significant temperature dependence. At higher temperature, that band becomes stronger. At lower temperature, the band becomes weaker. So, it turns out to be a hot band. So, if it is a hot band, then its origin is in 1 dash. So, this is assigned as a 1-0 dash transition. Okay, it is a hot band. So, if it is a hot band, if I try to draw the potential energy surfaces, I will just draw 2 levels, right, so that I do not goof up too much. This is the transition we are talking about, isn't it? This is a 1-0 dash transition. No, this is a 1-1 dash transition. This is a 1-0 dash transition. Okay. What will the energy be? This is E00 dash. Is that right? Energy difference between the 0th vibrational levels of the 2 potential energy surfaces. That is called the band origin. We have discussed band origin earlier while talking about this Fortran diagram and all. This is your band origin. And so, how do I get this? This band origin minus this energy, isn't it? Right? Minus this. So, I can write this as nu bar. When nu bar is the nu bar for vibration. I have written something else there, but that does not matter. Okay? Maybe I will call it epsilon 00. So, this epsilon 10 dash is epsilon 00 minus nu bar V. Alright. Now, look at the next band, the immediately next band here. So, as you see, it looks very much like this one, right? The structure is the same. So, that is ascribed to 0 1 dash. Do you agree with me that 0 1 dash should have higher energy than 1 0 dash, right? What is 0 1 dash? This is 0 1 dash, right? Just immediately next higher energy. What is that? Epsilon 0 1 dash will be band origin epsilon 0 0 dash plus nu bar V, right? What is nu bar V? This. Ideally, I should write nu bar V dash, because vibrational frequencies of the ground and excited states will not be the same. But as a first approximation, and as you will see in a while, we are really doing a very approximate treatment of the problem. So, as a first approximation, I will set nu bar V and nu bar V dash to be the same. Alright, so far so good. Now, see what I can do. Do I know the values of epsilon 1 0 dash and epsilon 0 1 dash? Do I know these values by some way? How? How do we know the values? Well, we have the spectrum, don't we? So, experimentally we can find out, read off from the spectrum what those values are. So, this here is the diagram that we have drawn. The only difference is here I have told you what the values are. The values actually are 37,483 centimeter inverse, 38,611 centimeter inverse. Okay? So, I know these left hand sides. So, what are the unknowns here? Epsilon 0 0 dash and nu bar V. Two unknowns, two equations. We can solve the two equations and find the two unknowns, right? I think that is child's play for us now. We do that. What is the approximation? The approximation is we are setting the two nu bar or nu values to be the same. That is the only approximation we have used. So, doing that, you just take add them up. You get a value of 262.8 nanometer for the band origin, and you subtract, that gives you the value of the frequency. So, this is what we have been able to do. First of all, even though we do not see the band origin in the spectrum, we have been able to work it out by this treatment, right. Have we done something like this earlier? Band origin that was not visible in the spectrum, we worked it out. Have we done this earlier? Nitai? Manoj? Where? When? You are right, we have done it earlier in this course. When? In which situation? Sorry? Ground state? Raman spectroscopy, or what kind of compound? That is also right. Sorry? Bird-Sponner extrapolation, yes we did. But even before that, you remember when we talked about this low vibrational spectrum, we had this PQ band, sorry PR band, Q band was missing, but we said that we can find out where the vibrational frequency is supposed to have been there, right, something similar. So, nothing new really. So, first thing we can do is we can find the band origin. Second thing that we can do is we can find the vibrational frequency, right. So, now we know that a vibrational frequency, a vibration with energy of about 564 centimeter inverse is the one that couples with electronic motion to make this transition vibronically allowed. What is the next step? Look at this table and tell me, is there anything that is close to 560? Is there any vibration in that table that is somewhere close? And when I say somewhere close, we can be very liberal about it. Yes, only one we can say is very close, and that is this last one, 606. Okay, and what is the symmetry of that? E to G. All right, and next part we are not going to do in detail, but just believe me when I say that there is no signature of B to G vibration anywhere in the spectrum, right. So, what does that mean? this band, this benzenoid band that we are interested in, becomes vibronically allowed due to participation of an E2G vibration. Now, if we go back to what we had learnt a little while ago, singlet A1G to singlet B1U is vibronically allowed not only by E2G, but also by B2G vibration. The other one is vibronically allowed only by E2G vibration. Okay? Well, there are a few steps in between, but for now we can just say that hence this benzenoid band is assigned to the second transition, alright. So, this is our spectrum. We had already assigned the strongest band to the fully allowed singlet A1G to singlet E1U transition. We have worked out that the benzenoid band is due to singlet A1G to singlet B2U vibration, singlet A1G to singlet B2U transition. Now, we are left with one orbitally forbidden band and we are left with one situation, right, another kind of transition, we assign it singlet A1G to singlet B1U. Okay. You could have also tried to analyze this. You might think, why is it that we are working with this and not that, alright. So, if you work with this, if you are lucky, perhaps you will be able to identify two vibrations, but it is easier to work with the benzenoid band because we have a well defined structure here. If you see this one, the structure is not really all that well defined because there is a significant overlap between two bands. So, it makes sense to work with the benzenoid band and then fill in the other one by whatever is left, alright. So, we are almost done with the assignment. The only part left is this. Now, if you look at phosphorescence spectrum, I think you are familiar with fluorescence and phosphorescence, aren't you? Are we familiar with fluorescence and phosphorescence? What is fluorescence? So, first of all, let us say it is an emissive deactivation pathway of an excited state. Both fluorescence and phosphorescence are emissive deactivation pathways of excited state. So, now tell me what is it that differentiates between fluorescence and phosphorescence, Juspinder? Okay, singlet excited state to singlet ground state, radiative, not radioactive. Radiative transition is fluorescence and triplet excited state to singlet ground states is phosphorescence, right? That is correct, but I would like to expand the definition a little more and make it more general. A radiative transition between two states of same multiplicity, same spin multiplicity is called fluorescence. Radiative transition between two states of different spin multiplicities is called phosphorescence. It does not have to be singlet-singlet. Triplet to triplet radiative transition is also fluorescence. Okay. Suppose you have something with a triplet ground state, then singlet to triplet will still be phosphorescence, triplet to triplet will be fluorescence. So, this is a more general definition that when you have a radiative transition between two states of same spin multiplicity, that is fluorescence. When the two states have different spin multiplicities, it is phosphorescence. It turns out that this weak band is a mirror image of phosphorescence spectrum and thereby it is assigned. So, you understand that it is a singlet to triplet, well, by both intensity and this mirror image relationship, it is a singlet to triplet kind of transition and we will not discuss further, but it is really singlet A1G to triplet B1U transition, right. That brings us to an end of the discussion of absorption spectrum of benzene and that is sort of the climax of what we wanted to do in electronic spectroscopy. So, we are done with electronic vibration rotation. In the last class, we might come back to rotational spectroscopy and we might talk about the influence of nuclear spin on rotational spectra and also the influence of symmetry on rotation, on population of rotational levels if we have time. But before that, next what we want to do is we want to now go to a completely different kind, apparently different kind of discussion, that is of NMR spectroscopy. Now, NMR of course is the most commonly used spectroscopic technique used by chemists and I am sure you have already been exposed to NMR spectroscopy, almost all of you in other courses, but still what we will do is we will start from the beginning, right. We have had so many classes, it is okay if we spend one class in revising basics. So, next day we are going to kind of revise our concepts in NMR, then we will talk about pulsed NMR, and once we are done with that, the end of not end really, the remaining part of the discussion of NMR spectroscopy will be the quantum mechanics of NMR. For that we will need to know the variation theorem, we will need to know time independent perturbation theory.